everyone. Today we are very happy to invite Dr. Uh, Goswami to come to give us this talk. And Dr. Goswami graduated in Indian Institute of Space Science and Technology as a master in 2015. And then he stayed in India as a junior research fellow for 1 year. And then he moved to Australia in the University of Queensland for pursuing his Ph.D. under the supervision of Dr. Jacqui. Uh, he just graduated and obtained his Ph.D. degree last week. So it's quite fresh. Very congratulations. And today he will introduce us his PhD work for us. So let's welcome him.
Okay, I'll start. Just let me verify my shared content. Okay. So my slide is visible, right?
Yes, it's good.
Okay. Thank you, Minshu and the team for introducing me. And I'd like to express my sincere gratitude for inviting me and giving me an opportunity to present my talk. I hope all of you are hale and hearty in this challenging time of pandemic. So today I'm going to present my works. Mostly the common theme is higher order quantum maps. So it has two specific applications. One is non-Markovian process. So the paper has been reported in arXiv, and I'm happy to announce that it has been accepted yesterday. And the other one is about indefinite causal order. So the first paper is on experiment and the second paper is on theory. So before talking about specific applications, let me introduce some pictorial notations that I'll be using throughout my presentation. So let's talk about elementary quantum operations first. So elementary quantum operations can be divided into three categories. State preparation, where I have some input state X and I'll prepare some quantum state rho X. State transformation, where an input state is transformed to an output state through a map. So this map, if this map is a quantum channel, it has the following properties. The first property ensures that a valid input state will always produce a valid output state. That is, the map has to be positive, and a more stronger condition is complete positive. The second condition, the trace preserving condition, ensures that the operation is deterministic. So these two conditions together is termed as completely positive trace preserving map, CPTP. And the final piece of the puzzle is state measurement, where an input state is measured using some, in general, POVM, and we get some classical output.
So excuse me. My slide, your presentation did not change. Is it only me, or is there a problem with your slide?
Yeah, I think it's not changing.
Yeah, because right now I can only see like higher order quantum maps, the first one. Yeah.
Let me redo it again. So just let me know if you can see the.
Oh, okay. Now it works. Okay.
Thanks for letting me know. Okay, so I was in this slide, so maybe I'll start over this slide again. So like I was talking about like elementary quantum operations. So like it is categorized into three like elementary objects: state preparation, state transformation, where a state transformation has two main properties: complete positivity and trace preserving condition. So together they are called CPTP map. And the final is state measurement, where an input quantum state is measured through some POVM and a classical output is obtained. The conditional probability of obtaining this classical output Y given the input state rho x is given by the Born rule. So these elementary quantum operations together can be formed to get a more general local operation. Like here in this example, I am showing a specific scenario where all three elementary objects have been used, and together it can form a new operation A. Note that here the output quantum state is dependent on the measurement outcome. This it's conditioned on Y. So the trace preserving condition in this case is not valid. However, it still produces a valid quantum state upon some normalization. So the the complete positivity condition is maintained. Okay, so this is the scenario of elementary quantum operation. A general CP map transforms an input quantum state to an output quantum state. However, we can talk about a more general higher order transformation known as process matrix or supermap, which transforms input quantum operations to an output quantum operation. So for example, if we so this higher order map W transforms this input A and B CP maps to an overall output complete positive map. So I'm giving some specific examples. So first is a typical bell-like scenario where the process is represented by the shared entangled state, and the local operation is performed by Alice and Bob. And okay, so this is a scenario where there is no communication. A second scenario is a communication without entanglement, where the process W is represented by this input quantum state and the CPTP map. So Alice and Bob performs operation in their respective laboratory, and the state is transformed to the output. And a more general scenario could be entanglement assisted communication. And this is a particular scenario of evolution with memory that I'll be talking after a few slides. Here, the process is given by this is given by this entangled state and a future CPTP map. Note that I'm using this inverted ground symbol, which is denoting discarding of the state. Mathematically, it is stressing out the operation. Okay, I have given some elementary introduction of the pictorial notations. Now let me talk about the non-Markovian process. Classically, a non-Markovian process is given by transformations of a random variable at different time steps. The evolution is Markovian when a random variable at any particular time is dependent on the random variable on in its previous time. However, it is independent of the past time steps. So as an example, I have shown this scenario where random variable at T3 given the knowledge of T2 is independent of T1. However, a more general scenario is possible where the transformation contains history of the evolution, and this general scenario is not this Markovianity condition is not maintained. we call such evolution as non-Markovian evolution or evolution with memory. So in quantum scenario, this is observed when there is interaction between system and the environment. Here rho is the system qubit, and at some time interval, after some time interval t1, it is interacting with the environment. Notice that when we measure the system after time interval t2, this measurement is dependent on the initial environmental state at t0. That is, the state depends on its history. So this is a particular scenario of non-Markovian process. Traditionally, such non-Markovian processes were characterized by dynamical maps. So for this particular example, the dynamic
Excuse me, is the video still going on? Hello?
It froze for me too.
sorry, is there?
Maybe the internet is broken for a while.
Hi.
Yeah, I can see you, but not your screen now. Okay, thanks.
Sorry for that. So can you see it now?
Yes.
And it's changing, right?
Yes, it's changing. So it's working now.
Okay. So like I'm not sure at what point the connection was interrupted. So
I think the next one.
Okay.
So here. Yes. You
okay.
can start.
Thank you. Yeah. Okay. So traditionally, the non-Markovian process is given by dynamical maps. So, for instance, in this particular scenario, the dynamical map is given by this green shaded area, and it is represented by the map after tracing out the environment. To characterize this dynamical map, we need to do state preparation. So this pi I is some projection operation that prepares the specific state, and at the end we perform some measurement. So this conditional probability given by Bond's rule completely characterizes this dynamical map. And so given this dynamical map, we need to have some condition for Markovianity. And this condition of Markovianity, so if a process is Markovian, then this particular condition called CP divisibility is maintained. So this is given by this particular equation, where a dynamical map at a future time step T2 plus T3 can be factorized into individual dynamical maps. So interested audiences are encouraged to look at this detailed review. And so we have this traditional description of dynamical maps. However, there are some potential problems with such formalism. So first of all, this condition of CP divisibility is not completely it's not complete to describe Markovianity or non-Markovianity. Specifically, there exists certain non-Markovian process which is CP divisible, but the Markovianity condition is not maintained. The other more severe drawback is when we have initial system environment correlation. So notice this in this figure, when we have initial system environment correlation, the state preparation on the system affects the environment as well. That means the dynamical map is conditioned on the state preparation, which is not desired at all. And because of this conditional dependence on the state preparation, oftentimes the complete positivity condition is violated. So that means the dynamical map loses its operational interpretation. To alleviate that issue, process matrix formalism is suggested. In this scenario, we only consider the background process, and this open slot is given by local operations, is left open for local operations. So these AI, AO, BI are the nomenclature of the Hilbert spaces. So to characterize this process, one need to perform a measurement operation at AI and BI and a state preparation at AO. So for a complete characterization, a generalized Born rule has to be implemented. So note that I'm using this transpose operation on sigma I and sigma j because for local operations we have to implement the Choi representation. So okay, so I have given some introduction of process matrix formalism and how we can use it to represent non-Markovian process. Now let's come to our work. So in our work, we are using a non-Markovian process. So in our case, the quantum system, initial quantum system rho is undergoing through 3 quantum operations, and at the end we are measuring the quantum system. So the non-Markovianity arises when there is correlation between the first and third quantum operation. This correlation is obtained by roll of dice. That is, we have a random variable, and based on this outcome of the random variable, we implement these operations. Note that whenever this joint distribution is not factorizable into its marginals, then we have a correlated random variable, and that leads to a non-Markovian process. So this is our specific scenario. Suppose we have a specific scenario of UX and UI. We choose these unitary operations from the Pauli group. The conditional probability is parameterized by this parameter q ranging from 0 to 1. Note that whenever q equal to 1, whenever q equal to 1, the operation ui is independent of ux and the process becomes Markovian. However, whenever q equal to 0, there is complete correlation between uy and ux. Additionally, we choose the marginal probabilities based on a bias R. See, this bias R represents how likely the operations are to be identity. So for example, high value of R represents more probability of the operations to be identity. And note that whenever R is very high, then UX and UI will almost surely be identity, and the process will again be Markovian. So the range of non-Markovianity will be low R and a value of Q closer to 1. Okay, so we have this particular process WXY for a specific implementation of UX and UI. And the overall non-Markovian process is given by this expectation of WXY. So how do we measure this non-Markovianity? This measure is given by given in this reference Pollock, and this S represents
Sorry, the internet is lag again. Hello? Anyone here?
Yeah, it's frozen for me too.
Okay.
hi. Sorry, there is some problem with this network. Am I audible again?
Yes, but can you change the
That's,
slide? See if it works.
yeah, sure. Thanks for your patience. It's, can you see the slide again?
Yes.
And it's changing, right?
Yeah, it's changing. Yeah.
Okay.
All right.
I sincerely apologize for all this. Okay, let's start again.
Okay, thank you.
Okay, so like I was talking about measure of non-Markovianity. So in our particular scenario, this measure is given by relative entropy, and this W Markov is obtained by in a way Markovianizing the non-Markovian operation. So the intuition behind this quantity is that every process matrix W is isomorphic to a quantum state. So for example, this tripartite process AI, AO, BI is isomorphic to a quantum state AI, AO, like three-party quantum state. And this particular quantity is basically mutual information between AI and AOBI. So this W tilde represents this isomorphism where this particular normalizing parameter represents the isomorphic quantum state. Okay, so we have given a measure, but now the question is how can we figure it out? So as I mentioned in the previous slides, that to have a complete characterization of the process, we need to perform measurement operations at AI and BI and state preparation at BAO. However, it turns out for a complete tomography, we need to perform several quantum operations, and like more complicated the process is, this number of possible quantum operations rises exponentially. So we aim to find a method to estimate this parameter, this measure non-Markovianity, efficiently. Here, efficiency means reducing number of operations. So we do that by implementing a unitary operation in the middle. This unitary operations is taken from a rotated Pauli group and performing a state tomography at the output. And based on the measurement results, we use a machine learning algorithm to figure out this measure of non-Markovianity with high accuracy.
Sorry, quick question.
Sure.
You treat the AOBI together, so are you assuming the non-Markovian only occur within the AOBI, and then AI to AO is only evolution? Are you assuming that?
Yes. So like for tomography, we need to have disjoint AI and AO, right? And so that increases number of operations. So in our case, we are using just state evolution. So just an unitary operation, and the background W is still non-Markovian because it is composed of this UX and UI, and it has this correlation.
Okay, thank you.
Okay. So, so this is the plan of our work, and we implemented an experiment. So for our experiment, we have chosen the following parameters for Q and R. So we have 10 combinations. For each combinations, we generated 100 probability distributions. That means we have total 1000 processes. So these 1000 processes we use for our like for each process we measure the data, output data, and we feed the data to a supervised learning algorithm. So this is our experimental schematic where we use polarization of light to encode the quantum state, and the transformations are obtained by these wave plates, half wave plate and quarter wave plates. And at the end, we measure the polarization state using single photon detector. So this is our result. We have this is the result of regression where we can see that a polynomial regression of degree 2 achieves the best result, best in terms of our high R2 value and low mean absolute error. So we also wanted to check what is the minimum size of data set that gives us a comparatively good score. So we see that okay, so like this LTD means training data set. That is, we have total 1000 processes. We divided into 700 training data set and 300 test data set. So of course 700 will have the best value given our total available data set. However, we can see our training data set of 210 can achieve a kind of good R square value. The difference between train R square and test R square is not that much. That is, it doesn't suffer from high overfitting error. And yeah, so this is to check the limited data set, limited training data set size. And we have used other machine learning algorithms as well. Two interesting observations are this k nearest neighbor and gradient boosting. We can see while k nearest neighbor has the minimum overfitting, that is the minimum difference between train R square and test R square, gradient boosting achieves high test R square values and test mean absolute error. However, it suffers from overfitting. So our conclusion is a polynomial regression of degree 2 works the best in our specific setup. So we reported this work and it has been accepted recently. And with that, our work on non-Markovian quantum process is described. Now let me move on to indefinite causal order. So indefinite causal order. So this is a scenario when, suppose let me give an example by a game. One morning I get up and decided to eat my breakfast in a specific order based on a coin toss. So if the result is head, I'll take a sip from my coffee and have a bite at my sandwich, and I'll be happy. And if the result is tail, the order will be reversed. So in our classical world, we can only have a definite order. However, the question is what happens when we have a quantum coin? Let me answer this question by a device called quantum switch. In a quantum switch, we have a control qubit given by this subscript C, and a target qubit rho t. The operations A and B are acting on the target qubit. When the control qubit is in 0 state, the order is B first and then A, and for 1, the order is reversed. However, when the control qubit is in a superposition state, we have a superposition of 2 different orders. So this work, quantum switch, has motivation in foundational aspect like quantum gravity, as well as it has some communication advantages. So we wanted to implement this quantum switch in our laboratory. So for that, for target qubit, we used transverse spatial mode of light. So this is basically shape of photon. So for Hermite Gaussian 10, we will consider it as ket 0, and for Hermite Gaussian 01, it is ket 1. The polarization is the control. So for diagonal polarized light, it will represent superposition of the control state. So we also need to implement our unitary operations. So we do that by a series of rotating prism and cylindrical lenses. The rotating prism rotates the spatial profile of the beam. So in the Bloch sphere, if you want to go from 0 to 0 plus 1, a rotation of the prism achieves this transformation. So on the other hand, the cylindrical lens pair imparts a 90-degree phase shift to ket 1. However, ket 0 remains intact. So for example, if you want to go from 0 plus 1 to 0 plus I1, then a cylindrical lens pair will do the job. So for more general unitary operations, this specific chain of optics elements will achieve our goal. So with that, we have our quantum switch. Note that this operation C is the polarization measurement at the end, and these small cubes are polarizing beam splitter. So it transfers the horizontally polarized light and it reflects the vertically polarized light. So imagine the control qubit is in horizontally polarized state. So in this case, it will go through B first and then A. Whenever the control is in vertically polarized state, then it will go through A first and then B. And a diagonal polarization will achieve the superposition of order. So this is the space-time diagram of our quantum switch. This long spread represents the long coherence length of our photon. That is, our photon source is temporarily indistinguishable, and this is the spatial location of the operations. Okay, so we implement a device that seems to achieve superposition of order, but we need to bulletproof it. To do that, we use a tool called causal witness. So basically, a causal witness, like witnessing causal order, is a separating hyperplane problem. That is, it is possible to find a hyperplane S indefinite that separates definite ordered process from an indefinite ordered process. And whenever the expectation value of this hyperplane S indefinite is less than 0, then we'll ensure that this is indefinite causal order. So this causal witness is a device dependent test. That is, we need to have a particular set of unitary operations A and B to achieve our result. So these are our unitary operations, and the upper pictures are showing intensity profile of the beam, output beam, when the input is Hermite Gaussian 10, and lower figures are the phase profiles. So okay, with that we achieved the causal witness. So ideally the causal witness is minus 0.248, and we experimentally measured minus 0.171, which is 18 sigma violation from a causally separated process. That is when the witness is 0. And we conclude that our quantum switch indeed has indefinite causal order. So we reported this work in this following reference, and it got considerable media attention, and I was very happy because it was like my first PhD project. And with a happy note, I wanted to explore more on this quantum causal structure. And so like I'm present the last theory project with Fabio Costa. So this is a scenario where we consider a process consisting of two parties, where the communicating parties are themselves in an indefinite causal order. So what's the motivation behind that? Let me answer this by a game called Guess Your Neighbor's Input. So there are two players in this game, Alice and Bob. Both of them receive some classical input from their background. They process it in their respective local laboratory and outputs some classical state. The game will be won when each player successfully guesses their neighbor's input. That is when A equal to X and B equal to Y. So what is the best strategy in a definite order scenario? Suppose Bob is in future and Alice is in past. So in this scenario, the best strategy for Alice would be to receive the state X and directly send it to the receiving party, Bob, and Bob will correctly guess it. However, as Bob is in future of Alice, so Alice won't know what Bob will receive in future, and her best case is to randomly guess it. So the probability of success is bounded by this value 3/4, and it is known as causal witness. Causal inequality. However, it turns out whenever there is a more general bipartite process which doesn't admit a definite causal structure between Alice and Bob, then it is possible to violate the causal inequality. So this work has been reported in this work by Oreshkov, Costa, Bruckner, and this is a motivation for our work because we can see like this guess your neighbor's input game is a communication protocol. So definitely this indefinite causal order is resourceful in some communication tasks. So the particular question we wanted to ask is whether we can attribute information theoretic aspects of communication. For example, we can ask what is the capacity of bipartite process or higher order process. So with that goal, we aim to formalize the information theoretic protocols. And first, we consider a classical communication, one-way classical communication from Alice to Bob without a predefined causal order. So so this is the particular example I have given at the start of my presentation. And note that in all these examples, this operation A and B are in definite order. However, so like it is also possible to have a scenario where the order of the operations are probabilistically changing. That is with a probability P, Alice is before Bob, and 1 minus P, the order is reversed. However, we call this process causally separable process as well. So it is possible to have a scenario where this a more general process matrix doesn't belong to this set, and in this scenario, this particular process matrix is said to have indefinite causal order. Our previous example of quantum switch is a particular example of such process. So okay, so with that we can introduce classical communication through quantum process. So first, let's talk about traditional communication through quantum channel. In this scenario, Alice receives a classical input X, prepares some state, quantum state, transforms it to Bob through a quantum channel N, and Bob does some measurement. So an important parameter for to quantify the information transmission capacity is called Holevo quantity of the channel. So we use this idea for process as well. So suppose this is a particular bipartite process. Alice and Bob performs some local operations in their respective laboratory, and this A, W, B together form a new quantum channel. And now we can use the concept of quantum channel to quantum process. With that, we have a Holevo quantity for process. So specifically, this is given by Holevo quantity of this channel N, and we optimize over the local operations. Okay, so now we should talk about different asymptotic settings, because the capacity of channel is dependent on these different encoding and decoding setups. So first, let us talk about product encoding and product decoding, where Alice and Bob's operations are product state. And in this scenario, the capacity is given by this single letter formula, and it is bounded by Holevo quantity of the channel. So this is the equivalent scenario of product encoding, product decoding of processes, and we have found a single letter capacity for process, and we established this bound. Next, we can have product encoding and entangled decoding scenario, where the receiving party Bob jointly measures the output, and it turns out the channel capacity in this scenario is exactly given by the Holevo quantity. So the following inequality holds, and for process we have found an equivalent inequality. So this is the scenario. And finally, we can have entangled encoding and entangled decoding, where the channel capacity is given by regularized Holevo quantity, given by the Holevo quantity of the asymptotic setting, and it turns out this capacity can overshoot the Holevo quantity of the channel. And this work is given by Hastings. And in our case, we have a similar setup, and we establish a bound for we establish this following inequality. Okay, so these are some primary inequalities we have obtained. However, there is one technical caveat. So for example, in our asymptotic settings, we have considered all the local operations to be the same. However, it is possible to have a scenario where in each copy we are using different local operations. That means we have a non-stationary channel. So to tackle this problem, problem of non-stationary channel has been given in these two papers. The first one is about classical scenario, and the second one is about quantum channels. And we alleviate this issue of non-stationarity. So to explain that, first let me talk about a particular simplification procedure. So let us focus on the Bob's side first. So in case of Bob's side, we have this rho x, A and W together form a monopartite process. And this following paper shows that any monopartite process is given by this overall process with memory where V1 and V2 are isometries. Now you can see the final isometry V2 is traced out. However, this isometry is a trace preserving map. So if the output is traced out, that means this isometry V2 is redundant. And we have this following scenario. And so it turns out entire information about this process W is concentrated in the red shaded area. That is, Bob's operation is redundant. And the Holevo capacity of the process for one-way communication scenario is bounded by a logarithm of Bob's input Hilbert dimension of Bob's input Hilbert space. dBi is the dimension of bi. Okay, so okay, and for bipartite, for a qubit scenario, this Holevo quantity is bounded by 1. Okay, so now avoiding non-stationary channel. So first focus on the Bob's side. Okay, so first focus on Alice's side, where suppose at a specific instance we have this channel AI. We can always have a scenario where we have an extended CPTV channel A bar, which is controlled by a quantum state rho I. And in the Bob's side, we can have a scenario because Bob's operation is redundant, so we can trace out the output system BO, and we can have some redundant state psi, and we can bypass the system BI to the output. So together this psi and this bypassing channel, identity channel, is given by B bar. So now we have a scenario where we have a process matrix transforming the input operation A bar and B bar to a new channel N A bar B bar and W. And so the input quantum state is given by this joint state rho I rho x, and a new POVM operation is given by composition of Fi and sigma y. And now this now we are avoiding this non-stationarity issue. Okay, so now I'll summarize different capacities. So for channel capacities, single letter capacity is surpassed by product encoding entangled decoding scenario, and which is surpassed by entangled encoding and entangled decoding scenario. So we have our equivalent process capacities. Product encoding and product decoding is again the lowest one, is the most naive strategy. Then we have product encoding entangled decoding, and we have entangled encoding entangled decoding scenario. We also have a situation of bidirectional communication. May I ask how much time I'm left? So
maybe 5.
okay, so I'll quickly summarize this bidirectional communication. Okay, so this is a scenario where in the previous setup we talked about one directional communication, but in a bidirectional communication both parties are trying to send information to each other. So this is more close to the scenario of causal inequality violation. And so we have our result for causally separable process. In a causally separable process, previously obtained inequality entropic quantity is given by this mutual information, summation of mutual information between X and A and Y and B. And it has been shown that if all the systems AI, AO, BI, BO have an uniform dimension D, then this following bound is maintained. So in our case, we have generalized this inequality in terms of Holevo capacity. And so here we are considering this single letter capacity formula. And we have shown that this following bound holds. And note that whenever dAI equal to dBi, then this inequality reduces to the previously obtained inequality. So this is the bidirectional communication. We tried to violate this bound for a causally non-separable process. We didn't find any violation. And we have extended this scenario for multi-party communication, which could be interesting in case of network protocols. Here, like I have n parties, each sending information to other party, and the background process we again consider causally separable. And we have this following bound: when all dimensions are equal d, then sum of the this single letter capacity is bounded by this quantity, and again no violation is obtained. So this the lack of violation prompts us to think whether this inequality is a universal one. So with that, I conclude my talk. In the first part, I talked about non-Markovian process, how higher order map efficiently encodes this non-Markovian process, and using tomographically incomplete dataset, we can efficiently measure non-Markovianity. The second talk is about a specific experimental realization of indefinite causal order called quantum switch. And in the third part, we formalized different information theoretic concepts for process. And we have shown that for qubits, one-way communication cannot surpass a conventional communication through channel. And for bidirectional communication, we have obtained new bound for causally separable process. And violation of this bound is yet to be found. So we conjecture this might be an universal bound. Thank you.
Okay, thank you for the very nice talk. So any question or comments? So may I ask, in the next part of your talk, you're talking about the causal indefinity, and you obtain the different bounds. So what's the origin of different bounds for the indefinite and the causal definite process? Is there any different, I mean, how does their bounds give us different situations?
So, sure. Are you talking about this bidirectional communication scenario? This
Yes.
particular slide that I'm showing. So yeah, so in this scenario, so first of all, this particular work by Milkin, they used some numerical search to find this bound, and this bound was given by this mutual information, sum of two mutual informations, and they have considered a general scenario where all the dimensions are d. So like we kind of independently obtained this bound because we were trying to formalize Holevo quantity of processes and what could be the bidirectional bound, and we found this one. And then like we noted that this is generalization of the previous bound, because generalization in two senses. First of all, this is summation of mutual information. However, this single letter capacity formula in our case is like more optimized version. And second is we haven't considered uniform dimension. That is the dimension of AI, BI could be different. So in these two senses, this is a little generalized bound.
Okay.
So like, are you asking about if that question is how this is more generalized, then yeah.
Actually, I'm asking more general questions. So what's the advantage of the non-causal non-causal setting? Causal indefinite setting. What's the advantage over other definite process?
Yes. Okay. So that's a good question. So
Are you changing your slide or not?
I'm going to change my slide. Just a moment. Yeah. So so right now, can you
see your slide change?
Okay. Let me reshare it again. Okay, so can you see this particular site, motivation, guess your neighbor's input?
Yes.
Okay, so this was our initial motivation because this particular advantage of indefinite causal order was given by a game. So like they have found a particular probability of success of this game. So in a definite order scenario, this violation is not, this bound is not possible to violate. So, however, in an indefinite causal order scenario, this a more generalized process is possible to formalize where this bound is violated. So that was our initial motivation to proceed because like two things. First of all, this is because this is sending signals to the other parties. So it's a communication protocol. So and the only difference is we have a process with undefined causal structure. So maybe there is resource in quantum causal structure that is yet to formalize. So so yeah, that was our motivation. So like to answer your question, was advantage. Well, a particular advantage can be seen through this game where indefinite causal order has more probability of success than definite causal order. However, for one-way communication, we didn't find any advantage. And for bidirectional communication, we tried to like formalize in terms of entropic quantities, but violation, we couldn't find a violation using like von Neumann entropies. So like for example, like maybe we can say using this von Neumann like von Neumann entropy is like Renyi entropy with a particular alpha equal to 2, right? However, this probability of success probability can be interpreted in terms of like a particular like mean entropy. So if we cast this problem in terms of mean entropy, then we'll have some advantage. But for particular von Neumann entropy, using von Neumann entropy, we didn't find any advantage. Yeah.
Okay. Yeah, I see. Thanks.
Yeah.
Yeah. Maybe one more question. In the sorry, there is a question from the audience.
Oh, it's
Sure.
okay. You go ahead. Yeah.
Okay, maybe I quick ask my question first. So in your non-stationary case, you try to find a way to bypass it, but in the B part, it looks like it's just bypass through the identity. And so in this case, does the causal indefinite still remain, or you, because in the BI part, it looks like just lottery didn't have any effect. So I'm not sure if the causal indefinite can still there.
Yes, because like we have our freedom to do anything in the local operations. This A and B are local operations. However, the causal structure, whatever like we mean by that, is encoded in this background process W, this this shaded area, this gray shaded area. So so that's the point. Like in our local operation, we can do anything like state preparation, discard, measure and prepare, whatever operation. However, depending on the background process, the causal structure is like relevant. So like like bypassing this local operation like doesn't change the causal structure background
Okay,
process.
I see, I see. Thank you. And maybe Devi have question.
Okay, I think I have two to three questions. Okay. Oh, can you hear me?
Yep.
Okay, so one question is about okay, when we talk about this.
Sorry, Devi, your voice is not large enough.
Okay. Wait, give me one. 15 seconds.
Hi, David.
Okay. Yeah, I'm back. Okay, is this better?
Yeah,
Yeah.
this
is okay. Okay, so okay, so when we talk about this non-causal, okay, this process matrix, I have two things in my mind. One is more of a theory aspect, and one is more of a reality aspect. So let me put it this way. So so should the communication? So one aspect is that the communication should be modeled in this non-causal form instead of the usual causal form. So this is one interpretation. And the other interpretation is that, so, okay, maybe doing these non-causal, all right, let me try again. So one thing, so when we communicate, we have this communication channel, right? So one aspect is that, okay, this communication channel actually has something strange about it. There is some non-causal structure to it. So that's why I want to study this. This is one aspect. But the other may be that, oh, okay, so maybe having this non-causal structure actually brings us benefits. So we want to engineer some channel that has this kind of feature. So how would you comment on these two? So for me, it sounds like so for the theory paper that you were trying to explain, it's kind of suggests that the second idea, which is engineering these things because it has benefit, this idea doesn't seem to work that well. Is that an interpretation? Yeah.
Yes, definitely. Yeah. Because like our primary motivation was to find some possible resource in causal structure. So, for example, a more general causal structure, like indefinite causal structure, whether it can provide some communication advantage. And okay, so like we had another work on experimental work on quantum switch that I haven't presented, but like it turns out like there is some scenario where suppose like I have two depolarizing channels in a let's think about quantum switch now. Okay, so in a quantum switch, suppose I have two depolarizing channels with maximum depolarizing strength. So like you can imagine like when these depolarizing channels are in a definite order, then there is like no possibility of information transmission. However, like it turns out that when you arrange them in an indefinite order, like you can have some like non-zero capacity. So so there has been a like huge debate like where does this advantage come from? So so okay, we can discuss it later, but the point is that there has been an active interest in exploring resource of causal structure. So with that in mind, our theory paper is dedicated to that, like exploring the resource of causal structure.
I see. Oh, so for the depolarizing channel you mentioned, is that part of like one of your paper? Like I want to kind of look at it afterwards.
Yeah. Yes.
Okay. I think I'll go and find it.
Yeah. So we have done the experiment on it, but the theory paper was by Giulio Piribella. So
Okay. I see. Yeah, another short question is, so for the unitary, okay, so for the usual channel, we can think, okay, there is a unitary and there is this non-unitary in the sense that it's not invertible. So does this non-invertibility still transfer to these process matrix? So can I say, oh, there is some special type of process matrix which is invertible, but it's
yes.
not unitary form?
Yes, exactly. We can say that. So, for example, quantum switch, because there has been some work on reversibility of process. So, reversibility of process matrix. So, for example, quantum switch is a super map or process matrix which can be invertible, whereas this general like bipartite process that is like that violates the causal inequality, it doesn't have reversibility property. And interestingly, like it doesn't have a physical realization. Like we don't know a physical realization of a bipartite process, bipartite indefinite causal ordered process as well. So yeah, this is a good question, because there has been some work that shows a causal inequality can only be violated when the process is not reversible. So yeah, so to answer your question, yes, there are some processes which are reversible, some which are not.
I see. And one last short question is, so you mentioned there's a relation between mean entropy and some kind of success rate stuff.
Yeah.
Could you say a few more things, or what are some reference for that?
I mean, this is a speculation because, so like first of all, like the relationship between success probability and mean entropy, I think there is some like paper I have been discussing with Minshu as well, so maybe he can like direct you to a more relevant paper. So okay, so that's one thing. The other thing is like, why did I mention that? Because like because this question came to my mind, like we are finding these inequalities in terms of von Neumann entropies, so but we are not finding any violation. However, so then question comes, why then this causal inequality, this game is showing advantage? So I was thinking whether we are looking at the right quantity. Maybe some particular value of, from a particular value of alpha, we can start seeing this advantage. And in a limiting condition, when alpha is so mean entropy is alpha is 0, I guess, or 0 or infinity. I often get confused, but yeah. So in a limiting condition, we start seeing this advantage.
I see. Yeah, thank you.
So any more question or comment? Okay, if not, I think let's thanks Goswami again. Thank you.
Thank you very much.
Okay, thank you for coming.
Okay, thanks a lot.
Bye,
Nice
Minshu.
talk. Yeah. So yeah, this chat